Hello everyone, my name is Jinlei Zhao from Peking University. The paper I'm talking about today is exploiting the code knowledge graph for bug localization via bidirectional attention. My presentation will be followed as agenda shown on the screen. Firstly, in the process of fixing a bug, the quality insurance team will identify the bug through recording unexpected behaviors and writing down by natural language. Then the document is called a bug report. The bug report will pass to the developer, and the developer have to read and understand it to find his location. However, this process is very heavy time consuming. It is especially for a software which contains hundreds and thousands of files. So bug localization is aimed to automatically localizing the relevant source file, giving a natural language descriptions of bug within a software project. Simply, bug localization can be divided to traditional model and a deep learning-based model. The deep learning-based models recently shows a great improvements, but the difference in the syntax between the program language and the natural language still affect the performance. So this paper is study on the two aspects to improve the performance of bug localization. First, how to better represent the syntactic informations of programming language. Second, how to optimize the future instructor to bridge the semantic gap between these two languages. So for question one, our solution is provide the code knowledge graph with translating embeddings. For example, the file close always followed by the file open, and the doc write is always followed by the doc read. So to better represent the contact information, close and within the source file. Also, we turn this as inter-relation informations. We input the code knowledge graph to it, which shows on the right pictures. Well, we can see the node represent the code entities, such as the class, method, parameter, and the age represent their corresponding relations, such as instead of between the parameter and the class, and the heads between the class and the method. Then to improve the code knowledge graph to bug localization, we use translation embeddings. We use 3 of them in this paper. First, trans E, 1-to-1 relation, trans H, N-to-1 and N1-to-N relations, and trans R, which is space-to-space relations. Then for the second question, we defined the token from the code, which also appeared in the bug report as a keyword, and marked the corresponding lines as a key line. Then we hope the corresponding weights of key line are higher than the other lines. And also we call this attention is the keyword supervisor bidirectional attention. Then we use it to enrich the interaction information between the source file and the bug reports. Finally, combine 1 and 2, we propose our models KG bug locators shown on the above. So we can see the picture here. The part with number 1 is the code knowledge graph, and the part with number 2 is the keyword supervised bidirectional attention. And we verify our models on 4 open Java data sets. And table 1 shows the details of them. And also to better analyze our model, we'll go through 4 questions. First, can the KG bucket locator outperform the sorter in the bucket localizations? Second, how does the code knowledge graph affect the performance of a KG bucket locator and why? Third, how does the keyword supervised bidirectional attention affect the performance of a KG bucket locator and why? Last, which knowledge graph embedding methods are the best for the bucket localization and why? So for the question 1, we did a combination with 5 baselines, and we can see in the left table, the KG bucket locator achieve almost the best performance over other baselines, especially for the top 1 and top 5 scores. And it is worth to notice that the bucket locators is the only traditional baselines used here. And we find all the deep learning based models shows a huge improvements than it. For the question 2, we should study on the effectiveness of the code knowledge graph embedding. So firstly, we look at the table 3 in the right. We find without the code knowledge graph, our model, the performance of our model reduced a lot. And also, according to the dataset details, we find the code knowledge graph shows a better improvements for the dataset with a small amount of project sets. And to better show the effectiveness of the code knowledge graph, we also generated a case for it. Showing the left. So in this case, we find that the bug report is directly pointed to the preceding join points files. But actually, this bug should be related to 3 files instead of 1. Here, we use our KG bucket locators, use the code knowledge graph to build the connections between them, and finally did find of them for these bug reports. For the question 3, which is mainly studied on the effectiveness of keyword supervised bidirectional attention. Same as question 2, the ablation studies also prove the efficiency of our attention systems. And also a case is also generated to show the effectiveness. In this case, both bug report pointed to same files, and our KG bucket locators improve this attention to check the bug report specific features for different tasks, and finally did a successful label them correctly. For the last experiments, we tested the different translating embeddings methods for bucket localizations. According to this table, we find that the trans R achieve the best performance along them. And also we find that the trans R and the trans H, well, the trans H is 1-to-n and n-to-1 relation and the trans-I space-to-space relation showed a remarkable performance, which indicate that the relation between the code is much more complex than the simple text. So, and then in conclusion, so we are the first to involve a code knowledge graph to bug localization to exploit the interrelation informations. Second, we introduce a new attention called keywords supervised bi-directional attention to mine the interaction informations between the bug report and the source file. Third, we proposed a KG bug locator to leverage the interrelation and the interaction information for bug localization. And the result shows improvements over 5 sort approaches and on 4 Java datasets. And thank you for listening.